Good afternoon. This is Hakam Al-Asawi, Technical Support Engineer at Navy Engineering and Agencies. Today we're going to have an introduction to COMSO Multiphysics AC/DC module. We're going to talk about the module, its features, and what it can be used for. And we're going to perform a simple demonstration on how to use the features available in the module. First, talk about the COMSO Multiphysics AC/DC module. It's used for low frequency modeling for electric and magnetic fields. Some of the applications you might think of is motors and generators, electrical components, electronics, inductive heating, and machinery, different types of machinery. Some of the applications also include resistors, magnets, permanent or electromagnets, capacitors or capacitive devices, inductors and coils. Anything that has a core and a coil can be simulated using COMSO Multiphysics AC/DC module. Motors and actuators and electromagnetic heating, and depending on the Joule heating effect. The features you might find when you have AC/DC module are as follows. Some of them are under the resistive and capacitive, magnetic, and at the bottom you can find the Joule heating and induction heating. You can start with electrical currents and shells, electrical circuits, where you can model your electrical circuits by defining certain components, connecting one node to another, and thus completing your whole circuit. For example, if you would like to create an electrical circuit using some sort of transistors, resistors, inductors, and so on, and then connect this circuit to a certain type of coil like a speaker, you can do that using COMSO Multiphysics. You can also find the multiphysics part in the Joule heating, which includes electrical current and heat transfer in solids, or induction heating, which includes the magnetic fields feature and heat transfer in solids. The types of studies you can find included in this module are as you can find here. For example, frequency domain, stationary, time dependent, coil geometry analysis, and so on. As for the other features, you can find the COMSO Multiphysics AC/DC module is an additional feature in the part library where you can simulate magnets, coils, and motors. For example, you can create single conductor coils, homogenized multi-turn coils, and magnetic cores. By just defining certain parameters while selecting your part, you can create single conductor coils, you can see for these examples, or a multi-turn coil by just defining a certain type of geometrical domain, for example, a cylinder, a cube, and similar to these, or a hollowed out cube like that, and then specify what kind of wire gauge you're using and how many turns you have, and so on, and thus creating your multi-turn coil. And also you can find magnetic cores, for example, E cores and B cores. You can find all of these under the parts library. As for the demonstration today, we're going to start by switching our to COMSO Multiphysics window. Just a moment. So now we're going to start with our COMSO Multiphysics window. We can start by Model Wizard. We will demonstrate a bus bar with a Joule heating effect. So we're using a multiphysics this time. So we can start by Model Wizard, 3-dimension. I'm going to go to AC/DC, electromagnetic heating, and then selecting the Joule heating effect. You can also include Joule heating effect, Joule heating and thermal expansion if you would like to see what kind of thermal stresses develop in this body when heating it. So we can either select this or that. This is an extra physics which includes the structure mechanics part. We can also select this if you want. We click add, and we can see if we select this multiphysics, it's going to add the electrical current node, heat transfer in solids, and the solid mechanics part included with the multiphysics nodes that connects two of them in each. And then we can go to study. We can set stationary study and then click done. I can start by defining some parameters. For example, for voltage, I can define V1 as my potential difference, my voltage. For example, 0.1 volts, like that. And we can start with drawing the geometry of a bus bar. So I can use my work plane to create a bus bar. First, I can assign my work plane to be in the YZ plane, so instead of ZX, Y and Z, like this. And then I can start drawing on this work plane and then extruding it later. So first rectangle, I can change my units to length units from meter to centimeter. My width is going to be 5 centimeter and the height 1 centimeter. So yeah, this is what I get. So I just have a slice of 1 by 5 centimeters. What I can do now is to extrude it in the X direction. So extrude. Yes, extrude this work plane in this arrow direction, which is the X direction, for 10 centimeters. If I zoom out like that. So this is the base plate for my bus bar. And then I can use the revolve operator to revolve it 90 degrees upwards. And then instead of having it revolve the work plane, I can revolve this certain face. So I can select this face to revolve. And then I can check which axis I would like to revolve it upon. I would like to have it in this direction, 1, 0. So it's this axis. I can then push the axis a little bit up, which is half a centimeter up in the Z direction. And then select that I will just want it to revolve for 90 degrees. So yeah, I think I made a mistake here. Yes, something like that. So negative 90 degrees to revolve the other way. Yes, something like that. And then I can extrude this face upwards another 10 centimeters to conclude my bus bar. So extrude the face, that face, for 10 centimeters, like this. So this is how it should look like at the end for my bus bar. I can use the union operator. Make sure it's a complete piece, a unified piece. Next, I can select my material. So I can go to materials, add material. I can go into my built-in library. I can find a copper material. So this is the only domain I have, and this is why when I select copper is automatically assigned for this material. I can check also the internal material properties that are stored into console here. You can see all the values. If I would like to change any value, I can just click on it and change it. Either type it as a number, equation, interpolation, whatever feature I would like to use from the function part. I'm not bound to just scalar values. I can type anything into these fields. So going into the physics, for the electrical current, I can go to physics, boundaries, electrical potential, select this bottom part, apply my V1, and then go to boundaries again, select the ground, and thus I have my ground. So this is my terminal and this is my ground. I can run the model right now as it is by unselecting the other physics, or I can select all the physics later. So by default, everything is selected, so you can just complete the whole physics, defining the rest of my boundary conditions, and then run it at the end. For the heat transfer in solids, I would just like to define a heat flux surface, because by default, everything is insulated. You can see as for thermal insulation, all the faces are thermally insulated. I can define a heat flux for heat to escape. For example, I can say that everything is exposed to air, for example, and losing heat, or I can say that only a couple of faces are not insulated. So I can select this face, say convective heat flux, use external natural convection as a horizontal plate or in horizontal, yeah, like that, horizontal plate upside. And my characteristic length is going to be area over perimeter. My area is 10 centimeter by 5 centimeter, which is 50 centimeter square over the perimeter. So it's 20, 30, 50 over 30 centimeters. So it's 50 over 30. Like that. My surrounding fluid, we're going to assume it's air. And I'm going to keep the rest as is. I'm going to add another heat flux for the vertical wall or the vertical part of my model. So another heat flux. Same settings, but I'm going to select vertical wall or vertical plate. External natural vertical wall. The wall height is 10 centimeters. 10 centimeters. This automatically calculates the external natural convection from these walls without the need of user intervention. For the suction mechanics, if I leave the model as is, it's by default defined as a free floating model, so there is no constraints. So for example, if it expands or contracts or anything, there is no stresses will develop since everything is free. I can bind it from for example, two surfaces from here and there. Thus, when it tries to expand, it's gonna go in a certain direction, or I can bind it from here and there. So I can select fixed constraint from here and here. These are the two faces that it cannot move anywhere. They're fixed, anchored to an unmovable object. Thus, if it tries to expand, it's going to expand, for example, upwards or buckle in the middle, and then stresses will develop. Next, I can use the mesh. I'm going to use the automatic mesh or physics controlled mesh, and then I'm going to try to compute it. If I missed something, then it's going to alert me with an error message, and I can start troubleshooting it later. So the default plots were already plot now. You can see that we have a temperature plot, and then we have a stress plot. You can see the stresses developing near the constraints here and there. And also when it tries to expand, since you're constrained from these two parts, it's trying to expand in this right, like shifting to the right-hand side. If I change one of my fixed constraints, instead of having a fixed constraint here at 1, I can use it as a roller, for example. A roller is different from fixed constraint, so it can move on a certain plane but cannot detach from it. So if I assign a roller boundary to this one, so it can move in the y, negative y, z, negative z direction, but it cannot move in the x, negative x direction. And then try to solve it again. And you will find a little bit of a change in the stress plots. And then I can create whatever other plots I would like to have by going to results and then plotting them as we're going to see now. If I have an alternating current, what I'm currently simulating is a direct current, DC. If I have an alternating current, and you can use the frequency domain study and select what kind of frequency I have. For example, 50 hertz here. If I'm in the United States, I can use 60 hertz. So whatever frequency domain I can use, it's on my choice. So if you go back to stresses, now you can see the stresses near the edges here disappeared since it can go both ways. It can move around, but the stresses here are still there. It's just stuck. This face is stuck. It cannot move anywhere. So if I was saying if I wanted to create another result, another plot, I can go to results, for example, 3D plot group, use one example, use the multi-slice. Under multi-slice, I can select, for example, electrical current, electric, and then I can see the electrical fields developing in my object. You can see the electrical fields are different when you come to a corner. If my corner, if I have a sharp corner, the plot will differ. If I have a smooth corner or curved corner or a fillet corner, this is what it's going to look like. Also, you can see some anomalies into my results because I'm using a very coarse mesh element. If I increase the resolution of my mesh, see this is a coarse mesh element. If I increase the resolution, it's going to take a little bit more time to solve, but I'm going to get a smoother transition for the results and the color gradients. It's going to take some time to solve this time. I used to have 1,606 domain elements, as you can see here. Now I have 28,145 elements. So this will increase dramatically my degrees of freedom and the elements being solved, or the equations being solved. So if I go to study, add study, you can see different types of study which I can use. For example, frequency stationary and frequency transient. So if I use these frequency studies, I can include my electrical current with the frequency. So I'm using AC at this point. And for example, if I use frequency transient, I can also include a time domain. So for my frequency, I can type 50 hertz. And for the time domain, I can select whatever time domain for my study in seconds, hours, days, weeks, years, milliseconds, nanoseconds, microseconds, whatever. So this will help us to create an actual real life model, which is realistically close to whatever we're studying. I'm gonna try to solve the higher mesh, the high resolution mesh one. Yeah, the one before I had 12,000 and a half, 12,544 degrees of freedom. This one I have 174,000 degrees of freedom. So it should take some time. In the meantime, if anybody has a question, please use the raise hand function or ask a question in the chat box. It took 40 seconds more to solve it. So if I go again to my older plot, you can see that the color gradient is more smooth, transitioning from one value to another. Instead, it was a little bit jagged earlier. Also, if I use a better element in meshing, instead of, for example, triangular or tetrahedral in this case, I can use smoother elements like a swept mesh for this kind of geometry, optimizing the mesh at these curved areas to a finer element size, for example, and a coarser element size outside. I might get a better result plot or a better result depiction here. But for now, and this is a very simple model, I should not need something that complex or that advanced in meshing.